This lecture will be introducing transition elements, and a lot of this lecture will be review from the first quarter of general chemistry when we do electron configurations. So we'll be going through a lot of these electron configurations, which will probably be a little bit review for everyone. It's important, though, to get these electron configurations down because the electrons in these transition metals, that's where they get their properties from. So it's important to understand what those electron configurations are. Okay, this periodic table on the title slide is really, it's not very good, first of all, because this group is not lining up correctly with the transition metals. Okay, so don't try to use this particular table to do electron configurations because they'll be wrong. Okay, I made that mistake when going through this lecture, but why I included this one is because it gives these nice labels here. Okay, so when we talk about main group metals, those are the first two columns, right? And when we talk about main group non-metals, these are the columns over here in yellow. Okay, the transition elements or transition metals are these in the middle of those two blocks, and they're all labeled pink in this figure. Okay, so these are the ones we'll be discussing primarily. We'll also be discussing what are known as the inner transition elements, or the lanthanides and actinides, right? Each row of these inner transition metals has their own name, okay? And these get stuffed in between these two columns on the last two rows, okay? So that's where they're fitting in. They're not shown there usually ever, because that just makes the periodic table too wide to really fit on a page. So they're usually shown kind of down here with some sort of like an arrow or something up to these this point in here. Okay. All right, so the material from this lecture, specifically it's coming from chapter 23, section 1 and 2. Okay. Here's another view of a periodic table. Okay, this one's better because it's showing you the actual positioning of these rows in the main group nonmetals. Problem is they don't actually show you what those elements are, so this is not very useful to use either. It's just useful to point out the position of the transition elements. Again, they're in the middle of the periodic table where it gets kind of lower. The height here is lower. The other thing I wanted to point out with this figure is that those main group metals we refer to as the S block. The main group nonmetals we refer to as the P block, and that's because those are where the valence electrons are, what orbitals they're in. So here they're in the S orbital, here they're in the P orbital. Transition elements or transition metals we refer to as the D block. Okay? And that's because, again, their valence electrons are in the D orbitals. The inner transition elements are referred to as the F block. Now we actually see and use F orbitals. Their valence electrons are filling the F orbitals. Okay. The other thing I wanted to point out is the numbering of the columns or families in the periodic table. So just a reminder, when I say family or group, I'm talking about columns. When we say period, we're talking about row. Okay. So in the numbering system for the columns, the old way of numbering it involved a number and a letter. So 1A, 2A, 3A, 4A, 5A, those are the numbers for main group elements. And then the transition elements start here at 3B. Okay, so you go 1A, 2A, 3B, which is, I guess, fine, right? But if you go all the way up here to 7B and then to 8B, all of a sudden 8B is now 3 columns. Okay, that's kind of weird. And then the last 2 columns in the transition metals are 1B and 2B. So it just gets, using the old way of naming families gets very confusing for transition elements. So I'm going to try to use just the regular old number in parentheses, which is the exact number of the column that you're in. Okay, so just wanted to get that out of the way, because a lot of times you do see these references to the old nomenclature, and it can be a little bit confusing. Okay, so what are the properties of the transition metals? Well, all of these transition elements are metals. Okay. The main group elements, they can be metals if you're, on the far left of the periodic table. If you're on the far right, they're nonmetals, and then they're kind of like a mixture in between there. But for transition elements, they're all metals. Okay. If we look at the compounds they make, transition metal compounds tend to be colored and paramagnetic. So what paramagnetic means is they have unpaired electrons. Something that's diamagnetic does not have any unpaired electrons. So that's what those terms mean. So transition metal elements, when they form compounds, tend to be colored and they tend to be paramagnetic, have unpaired electrons. Transition that with main group ionic compounds, so a compound that's made between a metal and a nonmetal, of main group metal and a main group nonmetal, they're going to be colorless and diamagnetic, so no unpaired electrons and no colors. We'll talk a little bit about why that is. Okay, the properties of transition metal compounds are going to be related to that electron configuration of the metal ion. So that's why it's important to be able to remember how to write these electron configurations. This figure in the book just shows you kind of the difference of how these look. So we're going across that fourth row of the transition elements here from scandium to zinc. And you'll see that they do look different. A lot of them are silver or gray, but then you have some like iron and copper that have a little bit more color to them. And the size and shape of that these metals make also can vary quite dramatically. The electron configurations are really what's important for these in depicting their physical properties. So the D block, or transition metals, have the general condensed ground state configuration. So remember what that means. Condensed means that you're using the nearest preceding noble gas, and you can depict that in brackets. That depicts the core electrons, right? So you have the preceding noble gas in brackets, and then how the general formula of how your valence electrons are in these transition metals would be N, which is the number of the row of the periodic table that you're in, S2, and then N minus 1, D to the X. Right, so remember, whatever row you're in the periodic table, the principal quantum number for D, the D orbital there, is going to be one less than the row of the periodic table. So if you're in the fourth row, you would have a 4s2, and then the D orbital for that row would be 3D. And then X is the number of D electrons that you have. Okay. So X can be from 1 to 10 electrons in that D orbital, because you have 5 D orbitals, they can each hold 2 electrons. Okay, period 6 and 7 elements, those are where, remember where the lanthanides and actinides can stack in. Those can include that F sublevel. So their ground state condensed electron configuration is that preceding noble gas, NS2, and then N minus 2F14. So we've gone all the way through that column, or excuse me, that row of lanthanides or actinides, right? And the principal quantum number for an F orbital, a D orbital is 1 minus the row number. The F number is going to be 2 less than the row number. Okay, so N minus 2 F14, and then again N minus 1 D to the X. Okay, and again, this is for the 6th and 7th row of the periodic table. Okay. Transition metals generally form ions by losing the s orbital, or excuse me, the s electrons first, and then the d electrons. So that is probably the most important thing to remember on this slide, because we're going to be talking primarily about the positive charge versions of these transition metals. So the ions, where they've lost electrons, and to know what electrons are left, we have to be able to take electrons out of the correct orbitals. Okay, so the first 2 electrons a transition metal loses will be from those s orbitals. So just remember that. This figure shows the electron configurations of this 4th row, or the first row of the transition elements. Okay, their partial orbital diagrams are shown. Right, we go from scandium, which has 1 d electron, to zinc, which has 10. Okay, and the number of unpaired electrons are shown. Again, these are ground states, so these elements, elemental form, they're not charged. Okay. 2 things I wanted to point out here. The electrons fill the d orbitals one at a time. So you first, if we look at the from scandium to titanium, we're adding 1 more d electron. We add that to a separate orbital, right? We don't pair it with the electron that was already there in scandium. Okay, we're adding them to their own empty orbitals first until you get 1 electron in each of the 5 d orbitals. Then you start pairing them up, right? And so that's Hund's rule on how to fill the electrons. The other thing I wanted to point out is that you see something a little bit different from the general pattern here in 2 families or columns. And those happen at chromium, the family of chromium, and the family of copper. So for chromium here, you have, you would think you'd have 2 s electrons and 4 d electrons if you just follow this pattern. But you actually take one of those s electrons and move it to the 5th d orbital. So now you have a half-filled d subshell. So each d orbital has 1 electron. And it turns out that that's a pretty stable configuration, and so that's why that happens. That's why that 1 electron gets bumped up to the d orbital. And likewise with copper, right, you would expect it to have 4 paired orbitals and 1 electron in the last d orbital, but it takes an s electron to move it up there. So now you have a fully paired, fully full d subshell. Again, that's particularly stable. So the family of copper, to remember, that one's probably easy because you have that family is copper, silver, and gold in there. So that's usually kind of easier to remember, at least easier, I think, than the chromium family. Okay, so let's try a practice problem doing electron configurations. And I've included this periodic table here. It was not in the lecture slides, so if you're following along with the PDF version of the lecture slides, you probably have to go look up a periodic table when you're trying to work through these. And again, a reminder: do not use the one on the title slide, not positioned correctly, the main group. Okay, but if we're looking at this. Okay, we're writing the condensed electron configurations for the following. Okay, so the first one is zirconium, Zr. Okay, and this one here it's located right here. Okay, so the preceding noble gas would be krypton. Okay, and so I should probably just go through how I think about these. So I'm writing the electron configuration for zirconium. So doing the preceding noble gas, so if we work backwards, then the preceding row, that noble gas would be Kr, krypton. So we write that in brackets. Okay, and then we count electrons. So this is the 5th period or 5th row. So that would be 5s1, 5s2 for strontium. Yttrium would be now 4d1, and zirconium is 4d2. So we've filled 2 s electrons and 2 d electrons. Oops. So that is 5s2, 4d2. Okay, so that's pretty simple. Hopefully that's simple for the majority of the class, right? Because we've done that in the first quarter. The next two are ions. They're charged, they're positive charges because they've lost electrons. So these get a little bit more confusing. So if we look at vanadium, V, that's in the 4th row here. Preceding noble gas is argon. So this, let me just do vanadium 3+. Okay, the regular ground state, I like to write out what the normal ground state without losing electrons would have been. Okay, so that starts at argon. Then you go 4s1, 2, 4s2. And we count over 3d1, 3d2, 3d3. Okay, so that's how it would normally be. But we've lost 3 electrons. And remember, this is the critical point. The electrons we lose start with the s orbital. So we've lost 2 of the s orbitals electrons, and now we lose 1 more from the d. So we're left with 2. So this becomes, for vanadium 3+, argon 3d2. And then finally, molybdenum 3+, same, we're doing the same pattern, the same thing for that. Molybdenum now is down here in the 5th row. So its normal ground state configuration would be krypton 5s2, 4d4. But we've lost, again, 3 electrons. So 2 from the s, 1 from the d, and we're left with krypton 4d3. Okay, so that's how we would write condensed electron configurations for transition metals or transition metal ions. Taking that a step further, we can use these to tell if any of these ions are paramagnetic. Okay, and what that means, just to define it briefly, paramagnetic means you have unpaired electrons or unpaired spins, and diamagnetic means that all electrons are paired or all spins are paired. Right? If you have even 1 unpaired electron, it's going to be paramagnetic. No matter how many paired electrons you have, if there's 1 unpaired, it's considered paramagnetic. Right? So just because of that, you can see that most of these transition elements are going to be paramagnetic, right? Because the only time you're not going to have any unpaired electrons is when you have no electrons in the d subshell, or when you have 10 electrons in the d subshell to be completely paired. It changes a little bit when you talk about compounds, but for just the transition element ions by themselves, that's a rule you can follow. Right, so let's look at iron first. Right, iron, the normal condensed electron configuration would be argon 4s2, 3d6. Right, we're losing 3 electrons, which makes it become argon 3d5. Right, now we need to draw a partial orbital diagram to tell if it's paramagnetic or diamagnetic. So we only are considering the orbital of the valence electron, so in this case, only that 3d orbital. Okay, and we have 5 electrons, right? That's what that number is. So how do we put these in? Again, these are there's 5 d orbitals, and they go in based on Hund's rule, so 1 electron to each orbital first before you start pairing. So 1, 2, 3, 4, 5. Okay, is this paramagnetic or diamagnetic? Well, it's paramagnetic. You have unpaired electrons, and you actually have 5 of them. Okay, let's do nickel 2+ now. Okay, normally nickel would be argon 4s2, 3d8. And you might not need to actually write out what the ground state uncharged configuration is, but I tend to do that just because it's pretty easy and it's a safe way to make sure you're getting it right. Okay, so the +2 ion we'd lose those 4s electrons, so it'd just become argon 3d8. So again, we draw our 5 3d orbitals. Now we're putting in 8, so 1, 2, 3, 4, 5. We have 1 in each. Now we have to start pairing, so that's 6, 7, and 8. Okay, this one has only 2 unpaired electrons, but it still has unpaired electrons, so it's still paramagnetic. Okay. Trying to look at the trends either across a row or period of the transition elements or down a group or family, the trends aren't as, they don't jump out at you as much as they did for the main group elements, but we'll try to discuss a little bit of these trends. So as we move across a row or across a period, the following trends are observed. So atomic size will decrease at first as you go through the transition elements. Then it kind of reaches a constant level and remains sort of constant as you go through those transition elements. Right? Why that is that those d electrons are filling inner orbitals, so they shield the outer or s electrons very effectively. So those s electrons are not pulled closer as you step across each step in the periodic table. You're getting one more proton, so one more positive charge. Those s electrons aren't feeling the extra positive charges as much because you have d electrons that are shielding them from it. Okay, so the size remains fairly constant. Ionization energies also increase sort of little across the transition metals of a particular row. Electronegativities tend to increase slightly, but then they kind of decrease across that transition metal in a given period. So really, all that you can tell is that the atomic size sort of decreases a little bit, then remains constant. Ionization energies increase, but only a little bit across that row, and electronegativities increase, but only very slightly. That's sort of the general rule. So nothing really sticks out. And looking at that graphically, the transition elements are colored more deeper in these figures. So if you look, atomic radius is going down when we go from main group metals to the transition metals. But after that, you do a couple more steps and it decreases, and then it reaches sort of a constant there. Okay. Electronegativity, same thing. You're increasing, but then you sort of reach more of a constant level. And finally, first ionization energy is relatively constant, but you're slightly going up in general, although there's actually steps down out throughout the way, slight steps down. The really only one that looks much different is the last one. That ionization energy goes up, again, because you're removing an electron from a fully full, it'd be harder to remove only one electron from zinc, because then you're no matter what you slice it, you're either going to take out a fully full S shell or a fully filled D subshell. Okay. Now, if we look at the trends that were within a column or a group or a family within transition metals, the trends are differing from those observed for main group elements, just like when we look across a row. Okay, atomic size increases from period 4 to period 5. So row 4 to row 5, you see an increase in size in these, but that's not seen in row 5 to 6. So the size remains, it jumps from the first row to the second row of transition metals, but it stays relatively constant from the second to third row of transition elements. Okay. Why that is, well, the reasoning sort of shown here, that period 6 element has 32 more protons than the period 5 element. So you have much more positive charge added. Compare that to a difference of 18 for main group elements. So you have that more increase in positive charges, which pulls the electrons in closer. Okay. And that extra shrinkage from doing that is called that lanthanide contraction. Okay. More trends within groups. Electronegativity increases from row 4 to row 5, then generally remains unchanged from 5 to 6. So again, there's a difference between the 4th and 5th rows in the transition elements, but not in the 5th and 6th. Okay. The atomic size is increasing slightly down the group. Nuclear charge is increasing much more, and that leads to a higher electronegativity values, right? And that's the opposite of what it was seen in the main group elements, where if you just use the halogens as an example, fluorine is the most electronegative, and then as you go to chlorine and bromine, you're decreasing in electronegativities, so not increasing like you see from row 4 to row 5 of the transition elements. Okay. The density, which we haven't really talked about in general chemistry, density increases dramatically down a group. In that sense, the atomic volumes change very little, right? The atomic size is changing very little, but the atomic mass is increasing significantly. So the densities do go up as you go down the group. Graphically, this is how we can look at these, and these are looking at across a row in the periodic table with the tie lines connected. So this would be the first row of transition elements, or in the 4th row of the periodic table. Right, so for atomic radius, we do decrease slightly those first couple steps, then it remains pretty constant. Okay. Electronegativity, it's going up, but kind of slightly, and then you reach kind of a plateau. Same with the first ionization energy. In general, you're going up across that row. And then densities have this sort of half moon shape as you go across the row. Probably not that important to know that one. If we look at within a family, though, right, red is the 3D series, or 4th row, black is the 5th row, and blue is the 6th row, right? You can see there's a big jump between red and black, but not very much of a jump between blue and black for atomic size, if we're looking at just families. Okay, and that trend sort of can match some of these other, probably mostly, it's most obvious with atomic radius within a family, for how row 4 and row 5 are different, and row 5 and row 6 are not very different. Okay. Density, though, you can see that you're getting these big increases in density as you go from red to black to blue, so down a family, getting much, much more dense. Okay, so oxidation states, or oxidation numbers, are very important for transition elements. And unlike main group elements that we can tell what their oxidation state is based on what column they're in the periodic table, it's a lot harder to do that for transition metals. So for an example, the first row first column, main group element, main group metal, if it's in that first column, the oxidation state of that metal is going to be a +1, because it wants to get rid of 1 electron to get a noble gas configuration. Likewise, if it's in the second column, it wants to give up 2 electrons to get a noble gas configuration. Okay. Transition elements aren't really like that. They're not that simple. Okay, so most have multiple oxidation states. Okay, in general, there's kind of some rules to follow for them, and one of them is that the highest oxidation state, or the maximum number of electrons that a transition element can lose in groups 3 to 7, equals the group number. Okay, so for groups 3 to 7, columns 3 to 7, maximum oxidation state equals that group number. Okay, and the maximum state is really seen when you're combining them with very electronegative things like oxygen or fluorine that can pull all of those electrons possible away from them. Okay. Elements in that 8B group, or columns 8, 9, and 10, they exhibit fewer oxidation states, and then the higher oxidation state is less common and never equal to the group number. Okay. And in these, the +2 oxidation state is pretty common, and that's because it can lose those 2 s electrons, okay, pretty readily. Okay, so those all have the +2 oxidation state as a very common oxidation state. This is a figure showing how different oxidation number can affect the color of some of these compounds, transition element compounds. So these are all oxoanions, which means that the positively charged transition metal is combining with oxygen to make a negatively charged molecule. So manganese in the +2 oxidation state, so when it's not combined with an oxygen, okay, that +2 oxidation state for manganese gives kind of a pale pink color. But if we look at the +6 oxidation state for manganese O4 2-, that color changes drastically to a very dark green. And then for a +7 oxidation state, we're getting this purple. Okay, so you can see that there's a drastic change in the color of this compounds with the same exact metal, and it's because of the oxidation state. We'll talk more about why we get these particular colors when we talk about crystal field theory. So that'll be a few lectures down the road. Okay. An important thing to remember, though, as a review from general chemistry is how do we calculate these oxidation states or oxidation numbers. Okay, so for manganese 2+, right, that's easy. The oxidation number is just going to be the charge. Right? When it's in a compound now, it gets a little bit different, and that should be M. So manganese O4 2-. Okay. How do we get that oxidation number? Well, manganese can have multiple oxidation states, so we can't just pick an oxidation number for it. We first have to look at what's the other elements in the compound. So in this case, it's oxygen. Oxygen is always going to be a -2, unless it's in a molecule like O2 bonded to itself, or in a peroxide where it's bonded to another oxygen. But in all compounds, oxygen is going to be a -2 oxidation number. So the oxidation numbers have to add up to the total charge of the molecule. So if we just put an X for manganese, and we have -2 for oxygen, but there are 4 of them, so X plus 4 times -2, that has to equal up to -2, because that's our total charge on our molecule. Right, so doing that algebra, you can do the algebra, or you can kind of do it in your head if you're confident with it, but that gives a +6 oxidation state for manganese in this compound. Okay, so that's just a general review on how to do the oxidation numbers. Very important as we go forward in this class to be able to do that. Okay. The table here shows the different oxidation states these particular transition metals can have. So we're looking at, again, the first row of transition elements, so that row 4 from scandium to zinc. And you'll see at the ends, right, zinc and scandium can only really have 2 oxidation states, a 0 or a +3 for scandium, so it has 1 d electron or no d electrons in those states. And zinc is either going to be a 0 or a +2, so it always has that paired d electrons, so it's always diamagnetic also. Okay, the others can have much more, get more complicated, and the amount of complication kind of peaks here in the middle, and that's in row 7, excuse me, column 7 with manganese, right? We have all of these oxidation states possible. Again, just pointing out how crazy that old way of naming the columns, their families are. Probably best just to refer to them as those numbers in parentheses. Okay. A trend in metallic behavior in the transition metals, and they're all metals, so they're always metals, but it turns out that the lower the oxidation state of a transition metal, the more metallic it can behave, right? And that means, what does that mean? Well, that means when it forms a bond, the more ionic that bond is. So the lower the oxidation state, the more it behaves like a metal, and the more ionic bonding there is. So the more it completely gives up electrons and is a full positive charge. Okay. Covalent bonding occurs more frequently for higher oxidation states. So that would be considered less metallic behavior. So if you look at a metal that has a +2 oxidation state and a +4 oxidation state, the +2 oxidation state of that metal will be more metallic, and it will undergo more of an ionic bond, and the +4 state would be less metallic and have more covalent nature to its bonding. You can also consider talk about this in terms of basic and acidic. So metal oxides become less basic or more acidic as the oxidation state increases. So think in terms of Lewis acids and Lewis bases, right? A Lewis base will donate electrons, and a Lewis acid will accept those electrons. So you can kind of think of it in terms of that. Okay, this metal atoms that are in positive oxidation states have greater attraction for bonded electrons as well. So not just free electrons, but bonded electrons, things like that are in actual molecules, so they can be coordinating with bonds and not just electrons. And that's referred to as valence state electronegativity. And that increases compared to the zero oxidation state. So if we look, this table, probably not too important to note, but it shows the ability of these 2+ ions for each of these transition metals. So we're again going across the row, fourth row of the periodic table from titanium to zinc. They're all 2+. The ability of them to accept 2 electrons to become their solid metals, uncharged. And this is referred to as reduction potential. And so as you go across that row, you get less and less negative values for this. Not important to know that right now. We're going to be talking about electrochemistry later in the course, so we'll give a better description of what these actually mean then. So just introducing it now. Don't need to know this, though, for this first part of the class. Okay. It turns out that the color and magnetic behavior of compounds made with transition elements, those properties, the color and magnetic behavior, really depend on the electron configurations, right? And as we mentioned before, main group ionic compounds are colorless and diamagnetic. And that's because the metal ion has no unpaired electrons. It's given up those electrons fully to the nonmetal in that ionic compound. But transition metal ionic compounds are highly colored and usually paramagnetic, and that's because the metal still has unpaired electrons. Okay, so color and magnetic behavior depend on unpaired electrons. Right, so the only way a transition metal can be colorless or diamagnetic is when it doesn't have any d electrons or when it has a d10. Right, that's specifically for transition metal ions and not necessarily in compounds. Okay, so that's the transition metal ions by themselves. When we talk about crystal field splitting, we'll talk about metal ions that are in compounds or complexes, and then it gets a little bit different. Okay, so here, the book gives this figure that just shows, again, across this row in the periodic table, the colors of these compounds, particular compounds, can vary greatly. So you can get things that are sort of uncolored, or you can get things that are very deeply colored. If we look at ionization energies in this case, we're looking at that 6 column, so we're looking at a family now in the periodic table. The ionization energies, again, increase down from that, here it is, ionization energies increase all the way down the family. So from the first step to the second step down that column, your ionization energy is increasing. By doing so, because it's harder and harder to remove electrons, the reactivity is decreasing. So it's seeing sort of an opposite, an inverse relationship with ionization energies. And if you remember back from the main group elements, ionization energies actually decrease down a family. Okay, so that's different. That's opposite than what's seen in that main group. And also just something to point out, atomic radius here, from going from chromium to molybdenum, we are actually increasing the atomic radius there. So that's row 4 to row 5. Row 5 to row 6 now, there's no increase in atomic radius. They stay the same. Okay, so moving on, that was an introduction to transition metals. Now we're going to talk a little bit about the inner transition elements. Okay, the inner transition elements are kind of unique because they have names for particular rows. So the first row of inner transition elements are called lanthanides. Right? Lanthanides also have another name called rare earth elements. Okay, so in that rare, that's an old name. So you might come across this. If you ever see that's really just means you're talking about lanthanides. The rare means that they are relatively rare compared to some of the other elements in the periodic table, right? They're much bigger when they're made in the universe, right? There's much less of them because you need more complex elements coming together, fusing together to make them. So they're just more scarce. Okay. The atomic properties of these lanthanides really doesn't change very much across the row. Okay, their chemical properties are also very similar, so that's in one sense it's easy to remember. You don't have to remember any sort of trends with them. They're all sort of similar. Okay, most of them have the ground state electron configuration of xenon. Okay, xenon's going to be that preceding noble gas for that 6th row. Okay, and then we have 6s2, 4fx, 5d0. Okay. In reality, if you look up these ground state electron configurations, there's a lot of differences or exceptions to the general rule or pattern in electron filling. So I'm not going to hold you responsible for any of those or expect you to memorize them. But so just kind of remember the general pattern in which we would fill them. But in reality, they can differ quite a bit just because the energy levels of, as you get further and further down the periodic table of these different orbitals, the energy level differences get closer and closer. So you can have, you know, an electron kind of move up to the d orbital, or an s electron move up to the f, and like it gets more confusing. Okay, but not responsible for it in this class. Okay, actinides, those inner transition elements in the 7th row, those are all radioactive. Okay, and again, they all have very similar physical and chemical properties to one another. So you can remember the lanthanides, not necessarily radioactive. All actinides are. The +3 oxidation state is very common for both of these lanthanides and actinides. So if we try a sample problem, this one's from the book. We have an alloy made up of samarium, which is lanthanide, there we go, and cobalt, which is a transition element. Okay, the question's really asking about how many unpaired electrons are in samarium. Okay, so this alloy can form a permanent magnet because they both have unpaired electrons in them. And then the question's really asking about samarium, how many unpaired electrons does it have? So what you need to do to solve this is to find the ground state electron configuration and then do a partial orbital diagram. Okay, so the ground state would be xenon 6s2 4f6, so hopefully you can make it to that point. Then to do a electron configuration, partial electron configuration, we only care about the valence electrons, okay, and we fill the orbitals, right? And the order is 6s, 4f, 5d, 6p. And we only have to worry about the s and the f. Okay, so we have 6 f electrons. There are actually 7 f orbitals, so we have 1 electron in 6 f orbitals, so we have 6 total unpaired. So how do you tell how many orbitals you can have for each of these designated or lettered orbitals? It all stems from quantum numbers. Okay, and so L, the quantum number L, tells you the type of orbital you have. And L can be from 0 to n-1. So that's the possible numbers for L. And n is the principal quantum number. So the simplest type of orbital would be when L is 0. Okay, when L is 0, that's an s orbital. Okay, why is there only one s orbital? That comes from the m sub L value. The number of allowed m sub L values tells you the number of allowed orbitals. So in a sense, m sub L is an orbital. Right, so the rule for m sub L is that it can be from negative L to positive L in whole number steps. So if L is 0, m sub L can only be 0. So that's why there's only one s orbital. For p, L is 1, and m sub L can be -1, 0, or 1. So that's why there are 3 p orbitals. D is L equals 2. M sub L can be -2, -1, 0, 1, and 2. That's why there are 5 d orbitals. And then finally F, now F is when L is 3. M sub L can be -3, -2, -1, 0, 1, 2, and 3. Okay, so there's 7 F orbitals possible. Okay, so hopefully that's a little bit of a refresher on why the number of orbitals are the way they are. You can just memorize them, probably what most people do, but if you think about it in terms of the quantum numbers, it might be easier for you down the road if you somehow forget how many orbitals there are in each of these designations to come to that number. Okay, let's try a final practice problem. How many unpaired electrons are in the following lanthanides or actinides? So TB, okay, if you look at the periodic table, TB is a lanthanide, so its preceding noble gas will be xenon. Okay, and these are easier in the fact that they don't have charges to them, so we're just looking at the uncharged ground state. Okay, xenon, we have in that 6th row, 2 s electrons, so 6s2, and then we count over 8 spots in the inner transition lanthanide row, so that would be 4f8. Okay. So remember in 4f, it's an f orbital, so there are 7 orbitals in it, so 4f. And we have 8 electrons to put in there, so 1, 2, 3, 4, 5, 6, 7, and finally 8. We have 1 that's paired, and 6 that are unpaired. So 6 is our number of unpaired for TB. Pu, now that is actinide. We have preceding noble gas of radon, 7s2, 5f5. Okay, so we again make our 7 orbitals. Okay, it's now the 5f orbital. We place 5 electrons in it, and they are all unpaired, so that's 5. Okay, and finally CF is going to be also an actinide, so we start with radon, 7s2, 5f9. Seven 5f electrons to fill. We have 9 electrons, so 1 electron in each of the 7, and then 2 that are paired. So that leaves 1, 2, 3, 4, 5. Again, 5 unpaired electrons. Okay, so next time we'll move into the next section of chapter 23 and talk about when these transition elements actually form compounds. And that's referred to as coordination compounds because you have other atoms or molecules that are coordinating around a center transition metal ion. Okay, so let's try a practice question using lanthanides and actinides and determining how many unpaired electrons they have. Okay, so we have 3 elements to look at. The first is a lanthanide, the other 2 are actinides. So I have this periodic table here. I would caution that make sure that you're using a good periodic table for this purpose. Because some of them show La and AC, lanthium and actium, still up here. And then they start the lanthanides and actinides with Ce and Th. That's a little bit hard because counting the number of F electrons then gets confusing because you have to start up here and then move down. Okay, so I included this one because these are all together. Okay. So what we would do for TB, okay, it's a lanthanide, so that preceding noble gas will be xenon. Then we count over 6s1, 6s2, and then we have the 4f1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So it is, if we write that configuration, let me switch to my pen. Okay, this configuration now is just xenon 6s2 4f10, and then if you want to be complete, right, we would put 5d0, but don't really need that since there are no d electrons. We can write our 7 4f orbital, partial orbital diagram. We have, excuse me, it should be 4f9, not 4f10. We have 9 electrons there to put that in. So that's 1, 2, 3, 4, 5, 6, 7, 8, and 9. So 2 get paired up. That leaves a total of 5 unpaired. Okay, looking at plutonium, Pu, right? Now this is an actinide, so the preceding noble gas is now radon, Rn. So Rn is our preceding noble gas. We have 7s2 and 5f6, and again 6d0. Okay, so doing 1, 2, 3, 4, 5, 6, 7, 5f orbitals, and we have 6 electrons to fill. 1, 2, 3, 4, 5, 6. So they're all unpaired, so we have 6 unpaired electrons for plutonium. Okay, finally CF. CF is 4 steps further now, californium. Its noble gas configuration, radon 7s2, 5f10, okay, 6d0. And if we fill 10 F electrons, right, 7 go in unpaired, and then we pair up 3 of them. So that gives us a total of 4 unpaired electrons. Okay, so hopefully that is fairly easy to do. Right. So that's our review and introduction to transition metals and intertransition metals. Next time we'll be talking about coordination compounds, and that's in section 3 of chapter 23. What a coordination compound is when you have a transition metal ion that has other molecules coordinating or bonded, arranged around it. So the transition metal is in the center, and these other atoms or molecules are surrounding it or coordinating it.